Hey, how you doing? I am Professor Derek, and I am going to do some review for the MIME section of the FE test. My section that I'm covering is mechanical design and analysis. So, Dr. Deal, okay? The real Dr. Deal. Let's see here. The first problem that I'm going to cover is over mechanical springs. So, a helical spring is made from a wire of diameter is 6 millimeters, with the outer diameter that is going to be 75 millimeters. If the permissible shear stress is 350 megapascals, and the modulus of rigidity is 84 kilonewton millimeters 5 millimeters squared, find the total axial load. I got to find my total F that the spring can carry and the distance the spring is displaced. There are 10 total coils, and the spring is square and closed end. Squared and closed. So first thing that we need to do is on page 433 of the FE handbook, we see that our shear stress is going to be Ks times 8F d over pi d cubed. Now I need my d, and I have dO. My d is going to be dO minus my wire diameter. So my spring kind of looks like this from the top view. This is my DO. And I need this diameter here with my wire diameter. So like D over 2 with times 2, therefore it's D. So my D is going to be 75 minus 6, which is just going to be 69 millimeters. Now I need my Ks. My Ks from the handbook is going to be 2C plus 1 over 2C. C is going to be D over D. Let's start this off here. My D over D, which is 69 over 6, is going to be 11.5. This is going to be unitless. My Ks then is 11.5 times 2, which is 23. So 23 plus 1 over 23. So 24 over 23, 1.043, let's go 5. 1.0435. My shear stress, which is 350, right, pascals, times my Ks, 1.0435, times 8F, and my diameter, 0.069, all over pi, my wire diameter, cubed. I have that my 350 megapascals is going to equal 84886F. My F is going to equal it's going to equal 412 pounds. No, this is going to be meters. Yeah, newtons. And then now that we have our axial load, so here's my first part. I need the total distance that the spring is displaced. Therefore, I know that my force, which is 412, equals my K times X. My K, my little k, also from page 433, we know is wire diameter to the fourth times my modulus of rigidity over 8, my mean diameter of my spring times n. Now I have nt, but I need n. If we go down to the next page, 434, I see that my squared and closed, my nt for my squared and closed is going to equal n plus 2. Therefore, my n is going to equal 8 coils. That's my active coils, by the way. So K is then going to be 0.006 times to the fourth times my modulus of rigidity, which is 84 kilonewtons per millimeter cubed, or squared, not cubed, squared, all over 8. My wire diameter, which is my 69 millimeters cubed, times my number of active coils. This is going to be millimeters cubed, kilonewtons per millimeter over millimeters squared to the fourth cubed, third is going to be squared. Therefore, I'm left with kilonewtons per millimeter, which is exactly what I want for K. And that comes out to be 84 over 8. Kilonewtons per millimeter. If I want it in newtons per meter, which is what I have, multiply by 1,000 and then also by another 1,000. So this is now going to be 5.178 newtons per meter. And I know that my force, which is my 412, going to equal Kx. 412 equals 5.178x. My x is going to equal 79. I messed up a unit conversion. One moment here. There we go. Therefore, I've got 79.6 millimeters. That's my final displacement. Yep, perfect. Boards are terrible. Not a fan. I pause this. All right, next up is power transmission. This is on page, let's see here, 435 of the handbook, of the FE handbook. The C clamp shown in the figure uses a 3/4 inch by 6 Acme thread. Now this comes from Mech Design, which the like tables in the books, have more information. Usually you would be given more information on the FE test. So what that means is that my D is going to be 3/4, and then my pitch, which is not given, it's given from a table, is going to be a 1/6 of an inch. The friction coefficients are 0.15 for the threads on the collar. The collar, which is in this case is the anvil striker swivel joint, has a friction diameter of 0.1. D of my collar is, 1 inch. Calculations are based on the maximum force of 8 pounds applied to the handle at a radius of 3.5 inches from the center line of the screw. Find the clamping force. So it'll be like this. My force is applied here, right? Here is my radius, and then here's my thread. It's something like this, right? My force is applied here. It's going to twist down the thread. What is my force at that point? You can find that, or what is the force at the point? Therefore, from page 435, attention to raise, which is what we're going to use here. So my T of R is going to equal FD over 2 times L plus pi mu dm over pi dm plus mu L plus F mu, this is now the collar that I'm worried about over here, dc over 2, correct? Yeah. Sometimes these two frictions are different. For our case, they're identical. I'm just using mu instead of mu of the thread and mu of the collar. So first we have to find dm. I'm given d, but I'm not given dm. If you're looking at the threads, right, you're looking at something kind of like this. This is my diameter, but I want the mean diameter of the threads, which is this guy. My pitch is going to be from the beginning of one tooth to the beginning of the next pitch, which in this case is also L. That's what the handbook is using for the pitch, is they're using L instead. But threads are set up so the distance, right, like tooth depth, is the pitch over 2. That's just how they're set up. Therefore, my mean diameter is going to be my diameter minus my pitch over 2. I apologize, I had a phone call. So now that I have my DM, right, my DM is my D minus my pitch over 2, which is going to be 3/4 minus my 1/6 or 1/12, which is going to be 0.6667 inches. Mu L, okay. My torque is going to be the 8 pounds times the 3.5 inches, right? 28 pounds of force per inch. 28 is going to equal F, which we don't know. That's what we're finding. This is the clamp force, or F of C, plus times my dm, 0.66, say 67, over 2 times my pitch, which is L of 1/6, plus pi, my friction, my mean diameter, 6667. Basically just plugging everything in right now. 6667, 5, 1/6, plus my collar, 5, D of collar, which is 1 inch over 2. This is going to come out to be, I don't have to solve this again. .1525 F is going to equal, come on in. It's going to equal my 28 pounds of force per inch. Therefore, F is going to equal 28 over 0.1525, which is going to come out to be 183 pounds of force as my clamping force. Let's see here. If we wanted to find the efficiency of the screw, that's pretty easy too. It's not asked, but it's easy to find. It's going to be our F, so your force times your pitch, over 2 pi t, 183, my pitch, over 2 pi times my torque of 28. It's going to come out to be 17.3%. All right, next up is gearing. We have a set of planetary gears, okay? You're going to have a ring gear that is fixed, like this. And then you have 5 other gears. Let's do this. One in the middle, and then 2 secondary gears. So this is going to be gear 5. Let's go 4 and 3 and 4 and 3, and then this is gear 2. This gear is connected to an axle, right? Here's my input. And this axle is going to be spinning at 320 RPM. This gear, 3 and 4, are connected to the same shaft, okay, which is then connected to this shaft here. This is my output. And this we are going to find the angular velocity. I have N of my second gear is going to be 12 teeth. N of my third gear is 16 teeth. N of my fourth gear is also 12 teeth. We don't know N5. Therefore, I have to still find N5. Yeah, so this output, which is the velocity of this arm, we have to find. To find my fifth N, I can first find my D's, right? So my D of my third gear, or let's just do D over 2 of my fifth gear, is going to equal my D of my third gear plus the D of my fourth gear plus half of the D of my first gear. Basically, we're going to just find this radius right here. And then from this book, we don't know the D's at all, but we do have a number which is called the module, which is the same as like the pitch. The pitch is going to be 1 over the module. The module is going to be, I think it's, let's see, D over N. Therefore, since I know that all of these gears are touching, they all have the same module, therefore the same pitch. Therefore, my M's just cancel out, but I can say then that my D is going to equal Mn. If I bring this guy down, I now have Mn5 over 2 equals Mn3 plus Mn4 plus Mn, this is 2 over 2. My M's all cancel out. My 2, let's go 2 here, and that 2 is going to cancel out. Therefore, N5 equals 2N3 plus 2N4 plus N2, which is going to equal 2 times 16 plus 2 times 12 plus 12. 2 and 16 is going to be 32 plus 24, 36 plus 32, 20 equal 68, which is going to equal the number of teeth for my fifth gear. There's the first part that we have to find. My second part that I have to find is the angular velocity of shaft A. Yeah, what is the speed of shaft A if my input rotates at 320 RPM counterclockwise? Counterclockwise when being viewed from the left side. So counterclockwise meaning it's going to go into the board and back out of it. Well, I'll do that later. All right, from back to the FE handbook. By the way, that equation is on page 436. On that same page, I know that my velocity ratio is going to be the product of the teeth driving over the product of the teeth being driven. So MV is going to equal the product of the teeth driving, 12 over 16 times then 16 driving 12, and then times 12 driving 68. 68, and this is going to cancel out to be my input over my output, 12 over 68. My velocity ratio is 0.176. My velocity ratio also is going to equal the angular velocity of the last gear minus the angular velocity of the arm over the angular velocity of the first gear minus the arm. My last gear is 0, right? That is going to be my fifth gear. Therefore, 0 minus WA over my first gear, which is the 320, minus WA, is going to equal 0.176. When I do the math, I'm going to have, let's see, 6, 5, 8. The angular velocity of my arm is going to come out to be negative 68 RPM. Is that it? I think that's it. Yes, and then the direction, my input is going to be counterclockwise because these two are going to be mated in parallel, right? If one turns this way, the other has to turn this way. Therefore, my direction switches from counterclockwise to clockwise to then counterclockwise. But this guy is going to be inside each other like this. Therefore, if he spins this way, and this is not fixed, this will also spin the same way. So counterclockwise, clockwise, counterclockwise, counterclockwise. Meaning my velocity is going to be the opposite of the input. No. Counterclockwise, clockwise, counterclockwise, counterclockwise. It's going to be in the same direction as my input. If I'm correct. Counterclockwise. Yeah. Yep. So this guy is going to be positive. This ratio is technically plus or minus. That's where that negative goes. Now I will pause you once again and erase the board because it takes 10 minutes. So a small correction on that previous problem. I was looking at the angular velocity of the direction of gear 5 when I should have been looking at gear 4. Because gear 4 was fixed, it goes from counterclockwise to then clockwise back to counterclockwise. And if it would pull itself around the inside gear, it would then be spinning in a clockwise motion. So that should be negative instead of positive. Next question is going to be joining methods. Mostly on page 438, starts on 437, but 438. For this problem, this is from an old PE question, by the way. We have something that kind of looks like this. Right, so like here is my beam with a bracket on it. My bracket is going to have a force 4,000 pounds down, then it has 4 bolts on it in this kind of pattern here. The dimensions of the bolts are 2 inches from the side. This is going to be, just say that this is 2 and that this is 2. And then they are 4 inches apart. No, they're 8 inches apart. The distance from the first row of bolts to my force is going to be 12 inches. This is asking for the factor of safety of 3, what diameter standard bolt should we use? This gives us that the bolt grade is a SAE 5.2 bolt. The properties of that bolt, which are not given but should be given on the FE, this is once again from the PE, you would have tables to look at, is my S ultimate is going to be 120 with my yield as 92. This is KPSI, KPSI. Now automatically, because we don't want this thing to fail, we are going to look at the yield strength instead of the ultimate strength. Because at the ultimate strength, the whole thing fails, but we don't want plastic deformation. Therefore, you're only going to look at the yield strength. The properties of my plate are, it's a thickness of 3/8 of an inch. My SY is going to be 54 KPSI. The S ultimate is given, but once again, we don't care about that. All right, so the first thing that we have to do is go to page, page 439. At the bottom of it, you'll see like a little thing that has arrows pointing all directions. We first have to find our first force, which is F prime or F1, which is basically going to be your shear force divided by the 4 bolts. So my 4,000 over 4, that's really hard math, is 1,000 pounds going down. So if I have 1 bolt, let's do this over here. If I have 1 bolt, this is the average, is 1,000 pounds going down. LB. For my second force, the formula is going to be MR, so my moment, over the sum of my radiuses squared, which is going to equal my 12 inches times, let's take the moment about the centroid, so 12 plus 4, which is going to be 16 inches. So my 4,000 pounds times my 16 inches, and then times my radius. This is about the centroid, by the way. My radius is the same for all 4 bolts because it's a square. My radius is going to be the square root of 4 squared plus 4 squared, right? So 16 and 16. This is all going to be over the sum of my radiuses squared. Basically, that square root is going to cancel out. I'm left with 4 times my 4 squared plus 4 squared. 16 times 4 is going to be, this 32 times 4, which is 128. Man, I'm good. 4,000 times 16 times the square root of 32 over 128. This comes out to be a second force of 28 pounds. Now, if you see on page 439 that it has arrows pointing in all directions, and that is going to be the force that the bolts are going to feel, right? So essentially, the equivalent force due to this torque. It's not the resultant force that the bracket feels, it's the force that the bolts feel. And I am left with essentially 2 different types of circumstances. One of the circumstances is where my second force is going to be pointing in the up direction based on the 2 bolts on the left side, and the other version is when the second force is going to be pointed in the down direction. So let's look at the top left and the top right bolt. My top left bolt is going to look kind of like this. My second force like here with this first force, right, F1. And my resultant force is going to be here. And then the bolt in the top right is going to look like my first force coming down with my second force over here. No. I think I'm doing this wrong. One moment. All right, my apologies, I was doing that wrong. The bolt on the top left is going to have the first force going down, and then from the tip of the force, it's going to be going to the up and to the right at 45 degrees. F1, F2, with my resultant force coming off at this weird angle here. The bolt on the top right is going to have the first force going down with the second force going down and to the right, 1, F2, with my resultant force being bigger than the resultant force on the left side. Therefore, this is the version that I want to find when finding the bearing stresses, because that is the biggest force that will happen in this configuration. My F2Y is going to be my F2, so 2828 times we say that this angle is a 45, and I want the sine, is going to come out to be, I think, 1,000 pounds. Sorry, 2,000 pounds. My F2x is going to be 2828 times the cosine 45. Same thing, 2,000 pounds. Therefore, my F is going to be 2,000 pounds, right? The square root of this guy plus my 2,000 pounds, plus the initial force from force 1, my 1,000 pounds squared. This is going to come out to be 3,606 pounds. That's the guy that I want to use. Now I need to find the bearing stress on the shear stress of the bolts. Now this isn't given in this book, but for the PE test, technically your shear stress, right, is going to be your load over your area. But this shear stress, you use what's called the nomenclature instead of SY. You don't want to use that guy. You want to use SSY, which is going to be 0.577 of your SY. I don't think the FE is going to really care if you do that, but technically this is the right way to do it. Really, really bad. Therefore, if I know my P, which is the 3,600 pounds, my A, the area of the bolt, is going to be P over my shear, which is 3,600 over my SY of my bolts, which is this is 92. 92,000 times 0.577 over my factor of safety. My area is going to come out to be 0.2038 squared inches. 0.2038 pi d squared over 4. My d is 0.5094. Half an inch plus a 16th is going to equal 9/16 is the area of the bolt, or the diameter of the bolt that we want to use. Now we can check this by finding the shear failure of, the bearing stress of the plate. And we want to find the bearing stress of the plate because that is going to be my yield stress. The plate is less than my yield stress of my bolt. Therefore, if my plate is fine, my bolt's fine. My bolt's not going to fail. To find that, you just worry about your regular stress, which is going to be my force 3606 over my area that the plate is going to feel. That's going to be 3/8 in depth by 9/16 wide. And this is going to come out to be 17,092 pounds. I can verify my factor of safety by taking my SY of my plate, which is going to be 54 PSI over my 1792. This is going to come out to be a little over 3.15, bigger than my factor of safety of 3, which is what I want. I'm good there, therefore I don't have to worry about my bolt. The next one that I want to worry about is the bearing stress is the shocks. Is the stress due to the moment of my plate. So I'm going to start out with my sigma equals my over I. My I, that's a heck of a calculation, my moment of inertia. So the side view of my plate is going to look something kind of like this, right? I got my hole here, my hole here. This is going to be 2 inches. Here's going to be 4 inches. Here is my center of mass. This is going to be 8 inches, sorry. And my other 2 inches. My thickness is 3/8. My diameter of the holes is 9/16. The moment of inertia is going to be base times height cubed over 12, going to be 3/8 times my 12 inches cubed over 12, but minus my 2 holes. And to find those moments of inertia, I subtract 2 times the moment of inertia of my hole. So 3/8 times 9/16 cubed over 12 minus the distance that they are offset. That's going to be your area times d squared. I think you can find that calculation somewhere else in the handbook. I know that you can, in fact. I can't search it though on that computer. So 3/8 times 9/16 times my offset distance, which is going to be 4 inches, right? Half of a. And this huge guy is going to give me a moment of inertia of 47.24 inches to the 4th. I can go back to my stress. My moment is going to be the same, 4,000 times 16 times my y distance. So that's the distance of my axis to the top of my piece, right? So that's 6 inches over my moment of inertia, 47.24. It's going to give me a stress of 8,128 psi. Once again, factor of safety is n equals 54 over 8.128, which comes out to be 6.62. Therefore, that's also greater than 3. And I know that this bracket will not fail given the torque at 12 inches from the closest pole at 4,000 pounds.